And all right, it looks like we are going. So thank you all for joining us today for these office hours. This is part of our Hello IoT series, which ran last week and then is also running this week. In just a few moments, I'll share a link to the series page where you can find the past sessions recording as well as register for our final session, which will be tomorrow, followed by office hours on Thursday the 15th. Or sorry, Thursday the 22nd. I'm a week behind. Before I start, a couple other quick things to go over. Please take a few moments to read our code of conduct. We do ask that you please be respectful to everyone, including other attendees and our speaker. We want to have a welcoming and safe environment for all. If you haven't already, please check in using our event check-in, aka.ms/reactor check-in with event ID 13429. I've shared a few links to that in the chat, but I will do so again momentarily. Please feel free to ask questions using the chat, or you're welcome to come off mute and ask your questions that way as well. In the chat, we'll be sharing some links to the Reactor Meetup page and monthly newsletter if you're interested in checking out what other sessions we have today. And then finally, near the end, we'll be sharing a link to our Reactor survey. If you have a few minutes, we greatly appreciate your feedback. I will now pass it over to Jim.
Awesome. Thank you very much. All right, let me just get my screen share going. Great. Well, thank you, everyone. Thank you for joining me. This is I've got to do some maths now. The 6th of our series of 8 live streams we're doing last week and this week, all about our IoT for Beginners series. So today is an office hours live stream. If you haven't been to one of these before, these are a very much relaxed, free-flowing, ask me anything kind of session. Yesterday, I ran a lesson covering sensors and actuators, looking at some of the information about how they work, the way they convert kind of electricity into digital signals that you can then use inside your IoT devices, and then digital signals back to electricity to physical interactions that you can use to kind of interact back with the real world. So today is all about discussing that. It's very much an open forum. I've got a couple of demos I want to run. During yesterday's session, I showed you how to build a nightlight with a Weir terminal on Arduino, and it had a light sensor and an LED. When you covered up the light sensor, the LED came on. When you uncovered the light sensor, it picked up enough light, the LED went off. I'm going to show you that again today using a Raspberry Pi and our virtual IoT hardware. But other than that, today really is about you. It's about me being here to answer any questions you've got, discuss any points. We can go back over some of the discussion points that we talked about in yesterday's session, or I can kind of answer anything around IoT, anything about the series so far, any kind of pressing questions you may have. So I'll kick off with a few demos where I think about the kind of questions that you've got, and then you can add your questions in the chat. If you want to come off mute and ask your questions, please feel free to do so. I do ask, if you're not actually asking a question, can you please keep your microphone on mute, just because of background noise, dogs, delivery folks, gardeners outside, it's good to kind of keep the noise down if you're not actually asking a question. And if you find that we get busy in conversation and there's not an opportunity for you to actually speak, there is a put your hand up button you can use in the top of Teams, and I'll spot that and make sure we get time to get to everybody who's got questions. So for those who haven't seen this before, IoT for Beginners is our new... Well, actually, I'll start with me. Let's start with me before I talk about IoT for Beginners. I'm Jim Bennett. I'm an education cloud advocate at Microsoft. It's my job to help folks who are learning IoT be successful with Microsoft and the various Microsoft technologies. It'd also be nice if my camera actually focused on me. Oh, there we go, focused again. I'm all over the internet, Jim Bob Bennett. Feel free to reach out and connect. Twitter, GitHub, Instagram, LinkedIn. Feel free to reach out, connect, answer questions. I know a few of you already have. It's really great to kind of chat to you, learn more about what you're doing. But please, I'm here to help you with anything around your learning of the Internet of Things. So feel free to reach out. I particularly focus on the education space, universities, students, student groups. So if you're a teacher and you want to bring IoT into the classroom, please reach out. I can try and help you with that. If you're a student, you want to bring it into your study groups, you want to help learn it more, again, I'm here to help. So IoT for Beginners, aka.ms/IoT-beginners. This is our 24-lesson IoT curriculum that we've put together to help you get started with IoT from the ground up. We literally start with the basics. What does IoT even stand for? What are devices, dev kits, What kind of cloud services might you have? What are sensors? What are actuators? How do they work? We kind of really wanted to put the fundamentals together. This is not designed to be teaching you just particular Azure IoT services. We do use Azure IoT services, but this is more generic introduction to the Internet of Things. And this is kind of your springboard to learn the basics and then go deeper into various Azure IoT services using Microsoft Learn at a later date. So you want to see what it looks like. It says on GitHub, it's all fully open source, completely free, no cost to use this, no cost to use this in your classroom or with your study group. Just fork it, grab it and go. We have 24 lessons covering kind of introduction and then a series of projects that show the Internet of Things in real world scenarios from farming, logistics, manufacturing, retail, and then consumer IoT devices. All hands-on projects, you get to build something with each one that does a real world job, just using kind of prototype hardware. Now, in terms of hardware, I'm going to give a shout out to our friends at Seed Studios. They have made it easy to buy the hardware you need to do this course. We support 3 hardware options for working through IoT for beginners, one based around Arduino, one based around Raspberry Pi, and one using virtual hardware, which is simulated on your local device, so you don't have to spend any money on hardware if you don't want to. But if you want to get the actual hardware, aka.ms/IoT-beginners-kit is the place to go to get the hardware. If you follow that link, it'll take you to a page where you can buy the hardware in one pre-packaged kit. So you just say how many kits you want and Seed will ship you the hardware. We had a bit of fun yesterday where I think it was my mistake. I put IoT-beginners-kits, plural, and everyone got lost and that didn't work. So that one now works as well. So I've added that short link just so that next time I muck up the link, it will work for everybody. So with that, and this is what we went through yesterday. I love the sketch notes. Our sketch note artist, Nitya, drew some amazing sketch notes to help teach the concepts. Yesterday, we went through sensors, analog sensors, digital sensors, actuators, digital actuators, pulse width modulation, all that kind of stuff. And I built a nightlight using a Wio terminal, an Arduino device. So today, let's kick off with doing the same thing, but on a Raspberry Pi device. Let's kick off and actually build the nightlight that I built yesterday. So I'm going to start by just talking through the sensors that I'm going to use. So in yesterday's session, if you remember, if you were there, I used this Wio terminal, which has got a built-in light sensor. That white square there with a white circle and the black square inside it, that's a light sensor. Obviously, I'm using a Raspberry Pi, doesn't have a light sensor, so I'm going to be using one of the Grove light sensors. And this is it here. It looks a bit like an LED, and it sort of kind of is. Come on, focus. There we go. In some ways, it kind of is. An LED, you put electricity in and you get light out. This is a photodiode. You put light in and you get electricity out. It kind of works the same way. I have read that in theory, you can shine bright light on an LED and get some current through. So this kind of works the same kind of way. But this is what we're going to use to actually measure light. Now, this is part of the Seed Grove kit. So you'll see it's all, it's got a nice little socket on there. Plug a cable in one end, and we have a cable at the other end that we can plug into our Raspberry Pi. Now I'm just going to unplug my Raspberry Pi. Always good to have no power when you're connecting hardware. It's only a few volts going through this, but you don't want to accidentally fry a chip. Now with the Raspberry Pi, with the Grove system from Seed, you have this hat, sits on top, and you have sockets on there that you can then plug your different devices into. Now the different sockets have different purposes. So if I just zoom in a bit, let's see if we can see what's written on some of these. It's upside down. Let's pick the too many cables. Okay, I'll just unplug you for now. So what we have, you'll see we have up here PWM. That's pulse width modulation. So if you remember yesterday, PWM, pulse width modulation, is how you can send signals. You send a short burst of electricity to do something, then you pause. Short burst of electricity, then you pause. And that's how you would do things like controlling the speed of a motor. So the burst of electricity, motor spins a little bit, stop, the motor stops. Another again, spins a little bit, spins a little bit, spins a little bit, spins a little bit. Do it fast enough and you can change the speed of rotation of things like a motor. We also have, this one here is called labeled UART. That's a serial protocol for sending data one back and forward. So you can just send blocks of data. You use that for things like GPS devices where they stream back text to give you location information. Then we have a load of pins labeled D.
you can think of these new kind of scenarios made possible by cloud technologies. Data visualization, whether it's in real time, whether it's time series that you're going to investigate, looking in the past, and a huge amount of data has been stored. The extraction of insightful information thanks to models and machine learning and others implemented in the cloud through the analytics we just mentioned and talked about. It's
Sounds
something
like
that
it's not
gives
a
you
question. This is someone watching a YouTube
vision,
video.
gives visibility into your data.
Okay. I hope that wasn't a question. It sounded like someone was watching a YouTube video, though. It didn't feel like a question, so I've just muted whoever that was. If you have a question, obviously, please jump in. But that didn't feel like a question, so if I muted you incorrectly, please let me know. Thank you. So yes, so what was I saying? Digital pins. So these ones here labeled D are go back to my camera. These ones here labeled D are digital pins. So these are the ones you can send digital signals through the Grove hat to the sensor. So you want to send, if you're doing things like LED, for example, I said that was a digital actuator. You send on or off signals. You do that through digital ones. If you want to send a more advanced signal, or you want to read, say, from a device that combines temperature, humidity, and pressure, you want to read digital data. Again, you do that through a digital port. These ones, A0, 2, 4, and 6, these are analog. So they take an analog stream of data. So devices that measure data across a certain range. If you remember from yesterday, the light sensor on the Weo terminal, that sent a value from 0 to 1023, which is a 10-bit representation of the voltage that comes back. Again, we'll do the same thing with the light sensor and these analog pins. So these are the ones that will send data in that range of 0 to 1023. And across the bottom here, these ones are I2C pins. I2C is a protocol you can use to talk to multiple different devices and send data back and forth. It's kind of out of the scope of what we're going to talk about today. But if you work with IT for beginners, we do cover I2C in a bit of detail. I will also point out on the Grove hat, a little slit here. If you saw in one of the earlier ones when I was looking at kind of capturing a photo just to show you the kind of size of data you might get with a camera, I put a camera into the Raspberry Pi. This is a little slit so you can actually get the camera cable into the Pi through the Grove hat, which is quite nice. So I'm going to connect my devices now. I'm going to build a night light, so I need a sensor, and this is my sensor here, my light sensor. And as I said, this is analog, so I'm going to put that into the port here, which is port A0, and you'll see there's little sticky out bits on there, so it can only go in one way. Now, in terms of the actuator I'm going to use, again, it's an LED, same LED I showed off yesterday. So it's a Grove LED, same socket. It's got a variable resistor I can use to adjust the brightness of the LED. And as I mentioned yesterday, LEDs, they're light emitting diodes, and a diode is something that can send electricity one way only. So when you put the LED in, you have to mount it in a little socket. It only goes in one way, otherwise it doesn't work. And these ones, there's a little flat side on this side, the negative terminal, round on the positive terminal. So if you ever plug an LED in, it doesn't work, take it out, turn it round, it might start working. Your LEDs are digital, so I need to plug this one into, which socket am I going to be using? I'm going to be copying and pasting code because I'm lazy, and I can't remember what socket I actually, what socket was I using? I think I was using D5. Yeah, so I plug that digital socket D5. So again, same only goes in one way, and it goes. Now, one question for these could be, why is it the analog and digital pins are the same and go in the same way? And really the reason for that is some of these Grove devices share pins that can do digital and analog at the same time. So for example, the Weo terminal, this socket here can take both digital and analog when you set in code which one's there for. So you do have to make sure you plug it in the right socket, and there's no help for you. It's not like digital and analog have different pins. Okay, so in terms of coding this up, I'm just booting up the Pi. There's two ways you can code the Pi. I will show you both of them when it boots up. Are we connected? Let's just double check we're connected. Yes. So the first way you can code the Pi is actually directly on the Pi. I'm a big fan of Visual Studio Code. It's my preferred IDE. It does all the things I need. Fantastic IDE. Absolutely love it. Completely free. It's mostly open source, except for the product images, which are copyright Microsoft, and our internal telemetry, which just monitors how much people use the different parts of the application, so we can make decisions about the best things to work for and catch any bugs. And you can run VS Code directly on a Raspberry Pi. So you install it with sudo apt install code, and it just goes off and installs, which is pretty cool. So you can run VS Code directly on your Pi and use that to program the nightlight. Another option is inside Visual Studio, there's an extension called Remote SSH. So I go to Extensions Marketplace. Remote SSH, and this allows me to remotely connect to my Pi and code from my Mac as if I was coding on the Pi. So if I go in here and I use Remote SSH and I connect to it's Pi at 192.168.197.212. That's my local IP address for my Pi. This will go off. This will connect to the Pi. It'll bring me up a terminal on the Pi. It will allow me to browse the Pi file system, open up a folder on the Pi, and work as if I was on the Pi. I could debug, all that kind of stuff, just using a remote connection to my Raspberry Pi. So for example, if I go into here, in here, let's create let's create a nightlight folder. So this is using VNC, screen sharing my Pi. If I go back here, in my remote, if I open folder, you'll see, where are we? Nightlight. So that's the new folder I've just created. And so now I can actually edit this folder from my Mac, which is pretty cool. And I can install things like extensions. So if I wanted the Python extension, so I want to install like Pylance, for example. Actually, Python installs it. That was a bit out of date, but yes, that's all installed already on my Pi. So I can put things like my Python extension there and do all my things. So let's just create an app.py file. Pylance just updated. Always the way when you're doing a demo, updates happen. So at least it's not a restart my computer update. So let's restart the window. Get everything going. And I'm here connected to my Pi. Now, with the Grove stuff, there is, let's choose the right Python interpreter. That's what I want. With the Grove hardware from Seed, there is actually a package some code you have to install to get everything working. So there's a command you run that downloads the install script from the Seed Studio GitHub page and installs everything. Now, for those who've done Python before, there is a thing called virtual environments, which you use to kind of keep all the packages that you have installed isolated. So you kind of have separate sets of packages, separate Python versions, all managed quite nicely. I don't do that on the Pi, mainly because things like this Grove install script will install the Grove packages globally. And also with the Pi, I must admit, it's so easy to reflash an SD card and start again that I don't bother too much about keeping it tidy and using virtual environments. So certainly with the Grove stuff, everything's kind of installed globally anyway, so it's kind of not much point. So what we want to do, we want to build a nightlight. And so the first thing we need to do with the nightlight is actually start reading from the light sensor. So let me just grab some code to do that. So a couple of imports. Import time, we can use that to make a delay. And then we import the library for the light sensor that comes from the Grove SDK. I then create my light sensor on pin 0. If you remember, I connected it to analog pin 0. And then in a nice little while true, I read the light level, print it out, and then finally we'll just have a little sleep in there. You know what? Let's sleep for one. Let's sleep for one. So if I now run this, that's now reading a light level, 512, 510, what have you. And if I then cover up the light sensor, so I've got it hidden there. Okay, that's not making much difference. Maybe it's not very bright here. Let's bring it closer to a bright light. Yeah. You know what? It helps if I plug it in the correct pin, doesn't it? There we go. Let's actually move to the correct pin. Now, if I bring it up to the lights, you'll see the light level goes up. If I just kind of take it away from the light and cover it up, there's me plugging into the wrong pin. So, yes, I unplugged it and changed the pin while it was powered on. Please do not try this at home. So cover it up. You'll see we get low levels. Open it back up again. See we get high levels. So we've got light being red. It's an analog signal, so it goes from 0 to 1023 because it's a 10-bit representation of the voltage. Okay, so let's actually convert this into a night light. Let's take the light level and then use that feedback to control an LED. And again, with the Grove kit, it's kind of just as easy to do. Oh, put that in the wrong place, didn't I? This is one thing I love about the Grove kit is they have really great libraries for handling everything. So I don't need to worry too much about voltages, pins, that as much. I can just say, bring the light sensor, bring the LED, and it works. This is kind of the point I was saying yesterday, that the whole purpose of IT for Beginners is to teach you the Internet of Things, building IoT applications, not teach you electrical engineering. So we don't want to get down too low level. We don't want to worry too much about resistors and making sure you've got the right resistors in place for your LEDs so don't burn it out. We want to just plug it in, get it working, and then build big applications from this. So this is my logic here. I added the LED. I read my light level. If it's less than 300, the LED comes on. Otherwise, it goes off. Relaunch that. My light level at the moment is 200 something because my light sensor is pointing down. And you'll see, oh, so there's the LED's gone off because the light's too high. If I cover up the light sensor, LED comes on, uncover it, goes off. So I've just built a basic night light. I'm reading an analog signal. I'm reading a voltage from a photodiode, which is a device that light comes in, produces a voltage. I'm reading a voltage from that. I'm making a decision off the voltage. I'm using that to send a signal to an LED. And an LED is a digital actuator. So it only has two options, on or off. It sends high voltage or low voltage. It's not like an analog one. It's not like a dimmer switch. I can't choose the level of on or offness. I just send on or off. The only control I have is the potentiometer, the variable resistor built into here, which limits the voltage, allows me to control how bright that LED is, but that's just a kind of a hardware thing. In terms of software, I send the digital signal. So we've got an analog sensor, digital actuator, and that gives us our basic night light. So that's the first demo I wanted to go through, which is using the Raspberry Pi for this. So the second thing I want to do is actually do the same thing, but using a thing called Counterfeit, which is our virtual IoT hardware. So kind of show you how you can replicate the same thing without having actually having to buy any IoT hardware. So what I'm going to do, I'm just going to go to my desktop and create a night light, and then go into my light light. Now this one I am going to create a Python virtual environment, so that I can manage all my Python packages properly. So I'm creating a virtual environment in this nightlight folder. That's done. Let's just open this in VS Code. And let's create app.py. And choose the Python interpreter of my virtual environment. There you go. So I'm running some of my virtual environment. So that way, what a virtual environment is, if you've not done it before, is it takes a copy of the version of Python that you're using. You see in here, you've got Python, pip, the package manager. And then when you install Python packages, they get installed inside the virtual environment. So it's all self-contained. And if I delete this nightlight folder, it all goes away. So if I install a package now, it won't be available from outside this virtual environment, which is quite nice. So the tool we're using to do this virtual hardware is a tool called Counterfeit. So where is it? GitHub.com/Counterfeit. And this is a project here that creates virtual IoT devices. So we can install shims, which are packages that simulate things like parts of Grove Pi or the Pi camera, and then you can actually set up on a web page the hardware that you want. So let's just install this quickly, and I'll show you how it works. So install Counterfeit. Just take a few seconds to install it. It's installed as a Python package, but then becomes an application you can then run, and then you can access that locally. Let's take a few seconds to install. So while that's going, what I'm going to do is I'm going to actually zip back over here. Probably my copy and paste is not going to work, is it? It doesn't work from VNC. So actually what I'm going to do, I'm going to open up another VS Code window. Kind of just as a bit of a demo of how Counterfeit is designed to simulate real hardware. What I'm going to do is I'm going to go back to my remote connection. And I'm literally going to take the code that I wrote for my nightlight and pretty much use exactly the same code. It's got a few seconds to... Come on. Okay, that's still installing. Come on. Why do I get the feeling I typed the wrong IP address? Okay. Let's try that again. This time I use the right IP address. Connect out window to host. Pi at 192.168.197.212. Yeah, always helps to type the right IP address. There we go. That was here, home Pi nightlight. So this is the code I wrote on the Pi, and I'm going to literally just copy and paste this code into here. Cool. Oh, we'll just upgrade my pip actually. So this is the code I wrote, and this is the code for running actually on the Raspberry Pi with the Grove hardware. Come on, go back to that. Question. So you're not using a local host for a virtual env. What do you mean by that? Sorry. So yeah, this is all running locally. This is running on my Mac. This is running on my Mac. Not on the Pi. This is running on the Mac. And so sort of a virtual environment in a folder on my desktop on my Mac. So I am hosting it on my local device, if that's what you're asking. Cool. Excellent. Thanks. So what I need to do is so install Counterfeit. Let's just run Counterfeit. So I'll just type in Counterfeit to run it. That will get running. And let me just bring it up. And so this is Counterfeit. It runs on my local device. And here I can create the hardware that I need. So what I need to create for this is I need a light sensor. So I create light, and I can some sensors have units, this one doesn't, and I choose the pin. So I want pin 0 because when I built this in the Raspberry Pi, I was connected to pin 0. So I add a light sensor. And now the light sensor, it tells me my value range, 0 to 1023. I can set a value or I can pick a random value. So I could say I want to set this to say 500. That way, every time I call this sensor in code, it will return a value of 500. Or I could set a random one. I could say I want to do between, say, 200 and 400. And that way, every time it calls, it'll get a random number between 200 and 400. So that gives me a light sensor. And then what I need to do is actually tweak my code very slightly. So the code I imported from the Raspberry Pi used the actual Grove libraries. The code that I used to talk to Counterfeit is almost identical. I just need to make a couple of very small changes to it. First change I need to make is I need to actually install some Grove shims. So if I bring up a new terminal, it's another pip package, and these shims, this is basically a version of grove.py, the same Python library I use on the Raspberry Pi, but one that's designed, instead of talking to the physical hardware, it talks to the virtual hardware in Counterfeit. The next thing I need to do is actually start the Counterfeit connection. So I drop a bit of extra code at the top of my Python file here. And this tells it to connect to localhost on port 5000. The reason for this is I can actually run this on a different port or a different computer. So I could run this code from my Raspberry Pi with Counterfeit running on my Mac, and I'll just put my Mac's IP address in here to connect. And then the only other little change is a package name. So rather than coming from grove.grove light sensor, it's Counterfeit shims grove. And that should be all I need to talk to read from the light sensor. In terms of the LED, I just need to add an LED. So let's add one on pin 5. Let's set it to be, let's go for a nice orange color. So you see our LED is now not set. Let's set this to a random value of, say, 200, set that. So if I now run this code, oh, there we go. Hope I copy and paste correctly. If I run this code now, you'll see we're getting a light level of 200 back. So it's returning the value that's here. If I change this to, say, 500, set that. We go here, 500, 500, 500. If I set this to, say, random, it's returning a random level. So that's actually giving me back the data I want. And then you'll notice my LED here is going on and off, on and off. So as my value changes, it changes the LED. If I go to random and I go turn off random, go for value of 100, set that, the LED comes on. If I go for value of, say, 350, set that, the LED goes off. So this is exactly the same as what we were seeing on the physical hardware, except I'm not using any actual hardware. I'm just using a virtual IoT device. This all running locally, hasn't cost me anything, but I'm seeing an LED work. Is this Counterfeit installation still covered in the curriculum documentation? Yes, absolutely yes. Everything's covered in there. In fact, if I go back to lesson, so start with lesson 1, getting started. Lessons, the very first introduction to IoT lesson, there's actually, as you go through the curriculum, we have kind of set up your device, and then here we have setting it up, the virtual single board computer, instructions for setting it up. And then when you work through sensors and actuators, which is lesson 3, we go through here, use a sensor, virtual device, and that tells you how to set up the virtual light sensor. And then when we get down to actuators down here, use an actuator virtual device, it shows you how to get working with a virtual LED. So all the instructions are there, and everything we do inside this curriculum, absolutely everything we do, you can do with the virtual hardware. I wanted to make sure that nobody has to spend much money if they have to. So when we do farming, when you measure temperature data, soil moisture data, control a relay, that's all virtual hardware. GPS tracking, all virtual hardware. Using a camera, all virtual hardware. speech, text to speech translations, all virtual hardware. You can do the entire thing without spending any money. Same with cloud services. Cloud services can potentially be very expensive. We've tried to keep that as low as possible. So for the bulk of what you do, it's all the free tiers of the services. There are a couple that aren't free. You may need to spin up a container repository, for example, very briefly whilst you're doing edge deployments. But we're trying to keep the costs as low as possible. And if you follow the instructions and spin it up and then spin it down as soon as you're done, you're looking at kind of less than $1 in terms of the cost for running everything. Obviously, your mileage may vary, depends on how long you keep the thing spun up for. We try to keep the cost as low as physically possible. IT is expensive. Buying hardware can get very expensive. And certainly if we're targeting this, things like students or universities, academic institutions are badly underfunded, terribly underfunded. Please write to your local politician and demand they actually pay teachers better and pay education institutions a darn sight better. We don't need more planes and destroyers. We need more teachers and better education. So yeah, I want to keep this as low as possible. And just for everybody, really, if we can avoid spending money, that's a good thing. So that's kind of the demos I wanted to show off today, just the same as I did yesterday, but using virtual IT hardware and Raspberry Pi. So really, this is the moment for me to hand over to you. This is an Ask Me Anything session. So please hit me up with your questions. If not, we can kind of go through some of the discussion points. I'd love to hear your thoughts on some of the discussion points from yesterday. I teach computer science at high school and I probably have students share kits after they work with virtual hardware. Awesome. Now I'm really glad this is something that's of use to you. The Counterfeit project is something I kind of started just to help people with hardware. It's still very much under construction. It's still, and it doesn't have the best error handling and that kind of stuff. It's me putting it together because there was a need for it. So if you do Python, you want to get involved, you want to contribute towards this project, please feel free. If you want to add more sensors, you can raise issues for more sensors. Someone's even had an issue to support .NET. No, there isn't a plan to release a .NET version. But if there's anything you want, please raise an issue. Please ask questions. I'm hoping this is something that can really support folks who want to do IoT but are limited in terms of the cost of hardware. And also, Randy, if there's anything I can do to help you with your students, please get in touch. Connect on LinkedIn, whatever. Send me a message and let me know how I can help. It's part of my job to support educators, so I would love to help you. If there's anything you need from me in terms of this content, please let me know. Looks like the Grove kits is what about several other boards. Could this curriculum be adapted to those boards? I mean, yes, totally. So I picked one set of hardware, the Grove kits with the Pi and the Wii terminal, because I wanted something that's kind of all-in-one, all-encompassing that would lower the barrier to entry. And there's obviously, it's a lot of work to port it to different hardware. I'll be completely honest. There's a lot of work to port this to different hardware. It's taken months for a few of us to put this content together. But one thing we've said all the way through is this is open source. This is free. So if you want to take this and port it to your hardware of choice, you are completely free to do so. There's literally nothing stopping you taking this and rewriting it for whatever hardware you want. If it's something that you feel will be of benefit to other folks, then you can obviously submit a pull request back to us to add extra boards to the curriculum if so inclined. But it's there, it's free, it's easy for you to use. Bunch of 3Bs, as in Pi 3Bs. If you mean the Pi 3Bs, yes. I mean, I'm using a Pi 4 because I have stacks of Pis, and I work with the closest board that I can grab. So I mean, my 3 is a bit further back on my shelf than my 4s. So that was a 4. I have a 3. I don't know. I have a 3 somewhere. I don't know where my 3's gone. The curse of having too much IT hardware. But yeah, this will totally work on older versions of the Raspberry Pi. I haven't tested some of the original kind of 2s. but it definitely works on the 3s. Works over Wi-Fi or wired as well. So if you want to obviously connect to a wired internet, when you get to the internet thing, so things, it works on all the different platforms. Obviously, if you get stuck with anything, again, please get in touch. Raise an issue on GitHub if you try it with an older Pi and you get issues. Raise an issue on GitHub, and I will do my best to kind of help and support. So, oh, what's this one from Ed? Ed's been a regular at these sessions, so it's great to see you here again, Ed. Latest Magpie Magazine has Grove Kit Plant Rotator. Oh, let's have a look at this. If you haven't come across Magpie Magazine, it is excellent. It's a magazine from the Raspberry Pi Foundation. It's completely free online. The digital version is completely free. You can download that, or you can buy a print one, which obviously supports the Raspberry Pi Foundation. So I subscribe to the print one, and it's full of fun projects, all based around Raspberry Pis, Raspberry Pi Picos. Articles are excellent people. Tanya Fish, for example, she's a brilliant maker based in the UK. Great article on the stuff she does to kind of teach folks electronics. Digital do not disturb signs. Absolutely fantastic magazine that's here. I cannot recommend it enough, and say it's completely free in digital version, or you can subscribe to digital, download free PDF, there you go. Or you can get it on the App Store, or you can subscribe to it. They usually give you something like a free Raspberry Pi Zero if you subscribe to it. Camera's playing silly one once again. And I can't recommend it enough. It's one of my favorite light reads. It's great. But yes, this one from Ed, using Grove Kit here with a motor on there to rotate a plant. Oh, that's pretty cool. So I guess if you have a window, you have a plant, you're only getting sunlight one side. So if you constantly rotate it, you're going to get even light around the plant. That's really cool. So that's again using the same Grove hardware to control. Now that looks like a sunlight sensor, I'm guessing. Yeah. So this one here is a sunlight sensor. Let me just zoom in a bit. Yes, this is a sunlight sensor. This is similar to the light sensor I was showing off. In fact, let me just grab one. Is this it? Yeah. So this is a Grove sunlight sensor. I'll just stick it in the camera. So this is a Grove sunlight sensor, and it's got a little thing in the middle there. But this will measure light, infrared lights, ultraviolet light. It's great if you want to build something for checking, are my kids out in the sun on a hot sunny day? Are they using enough sunscreen? That kind of thing. So using a sunlight sensor here, I guess, to measure the amount of sunshine. And then it's rotating the plant. So this here is some kind of motor controller. Now you'll notice the motor controller is connected to the GPIO pins directly. So this obviously isn't a Grove component necessarily, it's connected to the GPIO pins. Using a robot car chassis, looks like it's laser cut out of wood. 3D printed. And then using a motor. That's a superglued wheel to a stepper motor. So a stepper motor is a motor where you move it in increments. So you can say turn like 10 degrees, 20 degrees. It's designed to move in increments rather than be continuous rotation. So what they've got is a stepper motor here that just turns it, grabs data. Okay, so grabs data with InfluxDB, pulls the data in, analyzes it on the Pi, and then does a job to visualize the data dashboard and rotates the thing. That's really cool there. Thanks for sharing that one. That's a really cool project. Yeah, 1 kilogram plant, so it's quite heavy. See something a bit of power. But that's really cool. And this is kind of one of the great things about IoT is you can build a fun project like this, but this has real world value in terms of digital agriculture. If you want to have plants need good sunlight, so if you need to rotate plants into the right place based off sunlight, this is the kind of thing you can have. So fantastic. Yeah, thanks for sharing that. But yeah, honestly I can't recommend Magpie enough. It's it is an awesome magazine. highly recommend that. Randy's question, are you going to work through all 24 lessons from this curriculum or reactor? Not right now. So this is very much an experiment. So I'm running, first 2 lessons were last week, lesson 3 was yesterday, lesson 4 tomorrow, and then the office hours in between to kind of have this kind of discussion forum. This is very much an experiment to see how much interest there is. I'll be totally honest, it's a lot of work to put together these sessions. It's it takes a lot out of you. I'm quite exhausted by the end of it, especially with the office hours. So we're going to try it last week and this week. We're going to see how well it goes down with people, and then there is a chance to run through all 24 lessons starting later on in the year, but we don't know yet. It all depends on, honestly, it's about kind of return on time investment. If I get 10 people coming every lesson, then that's a lot of work. So there might be better use of my time, maybe recording videos and putting those up on YouTube, something like that. But yeah, certainly if there's anything I can do to help you, especially with your students, if you need things like guest lectures or anything like that, I'm always up for that kind of thing. So I'm always up for helping folks. We're trying to put together, so like the slide deck, for example, I've got here. I'll just drop out and show what it is. We've literally taken the sketch notes and we are using these in a slide deck. So we've only got I think 4 of the lessons so far with the slide deck sketch notes, but we're actually building these out. So if this helps, again, you'll have access to slides you can use to help teach it in the classroom, which kind of is pretty cool, kind of visual learning. Is it being taught at secondary school level? So, I mean, this is new. We only dropped this a couple of weeks ago. And we are currently in conversations with a number of universities and high schools that teach this at kind of who are looking for IoT stuff to teach at kind of the upper end of secondary school for kids with a STEM background. I can't say anything more about it. This is not something that's the schools is not public which schools we're working with, but we are talking to some schools about it. I don't know how well they're going to take this content on because they're still kind of looking at it. It's still very much early days. So it only went live on the 9th, it was 11 days ago. But we're obviously happy to work with any schools who want to teach this. And I will say that if you're going to go down the Arduino route, you probably want to be university level students, because C and C is quite advanced, and when we talk about things like memory constraints and power constraints, it does get a bit more advanced. On the Pi side of things, upper end of high school, as long as the kids have got a reasonable understanding of Python, they should at least better work through sort of the first few sets of lessons. So if I go back to the original, let's blow this up full. That's gonna be too big, isn't it? So we look at kind of the whole roadmap of this. In terms of the first 4 lessons, the code I've written was just, you've seen the code. It's kind of very, very simplistic. That should be easy enough for high school kids. When we get on to predicting plant growth, again, we're just reading from soil moisture sensor, using that with a measure of growing degree days, and this is based off a project that we've built at Microsoft for middle school kids around digital agriculture. And then migrating to the cloud may be a bit advanced. This is something that obviously, as a teacher, it might be more demonstration side rather than them running. But obviously, we need to bring in the cloud IoT, the I is internet. We need the cloud things there, and then especially with diving things like security. That might be a little bit advanced, but again, it depends very much on your students. Location tracking, visualizing, a little bit JavaScript in here, you can copy and paste, that should be fine. When you get onto fruit quality detection, training these models up is in a web portal. The code for it is fairly simplistic. It's catching an image from a camera, sending it. When it comes to running on the edge and kind of the overall architecture of an IoT application, might be a bit advanced. That might be more of a demo than the kids doing it. Stock detection, it's just capturing from the camera, reading bounding boxes, and then the text to speech. For the text to speech one, running it on a virtual device is actually easier than a Pi, because there's libraries that handle all the microphone stuff for you. If you do it on a Pi, there's a few kind of low-level web calls you have to make. But yeah, you should better pick out most of this at high school level without any issues. Just gonna Narasimha, thank you for joining. I've just muted you because sounds like got some pretty cool music going on in the background. But I've just muted you for now. So yeah, so Randy, yeah, totally. Most of this you should be fine teaching. Obviously, you know your students better than I do, so adjust the level of the content you're teaching to them. But if they've done some Python, if the code I've written here doesn't look too scary, then it's not going to get much more advanced than that. Awesome, cool. Any more questions? Anything anyone wants to ask? So these office hours are for you. They're for me to help you with any questions. If not, I'm going to start putting some questions to you. So let's start with the first question that came up. In fact, I'll do it from the slide so it's bigger. One of the first questions that came up discussion thing. I mentioned that phones can be considered to be IoT devices. They have sensors, they have actuators. So what sensors does your phone have? Do you want to start, people, if come off mute, shout it out loud. If not, in the chat, what sensors does your phone have that allows it to act like an IoT device? An open question for anybody. Come off mute and shout or write it in the chat. Camera, yes. Very much camera sensor, captures light data. GPS, yep, location data. Any others? Gyro, yes. Accelerometer and gyroscope, yes. Yeah, use those a lot. Just things like some apps you shake to undo is all picked up from accelerometer, and then the gyroscope magnetometer for the compass for directions. Very important when combined with GPS for location. Yes. Any others? Microphone, yep, very important sensor. Phone won't work without it. Light sensor, yes, that's one a lot of people overlook actually. So the main use of the light sensor on the phone is for ear detection. So when you have your phone, you have a screen that's capacitive touch and you touch it and things happen. But when you hold it to your ear, you don't want your ear to press buttons. And so it uses a light sensor to measure. But when it's against your ear, there's no light, and it actually disables the screen so you don't accidentally touch it with your ear. So that's, yes, very important sensor. Also used for things like screen brightness. It measures the amount of light and that can adjust how bright and dim the screen is. Fingerprint sensor, yep. A lot of devices have fingerprint sensors. Again, it's reading data, it's converting a physical value, your fingerprint, to electrical signal that is interpreted. Yep, magnetic compass. Yep, accelerometer. It also has a temperature sensor in it. Most phones have a temperature sensor. You don't normally see the result of this, but if you ever had your phone on the dashboard of your car using its GPS on a really hot day and have it shut down, which I've had that, it actually has a temperature sensor in it. Internally, if it overheats, it will actually slow itself down or shut it down. So yeah. Temperature sensor is another one. Trying to think what else it has. NFC, yep, some have NFC sensors. Well, that's actually one I use a lot. I'm a type 1 diabetic, and I have, I'll show you if you can see how we can see on the screen. I have this little device on my arm, measures my blood sugar and reports it through NFC. So in itself, it's just a separate sensor, a disconnected sensor. I take my phone, and I can take a reading from that sensor, and that gathers data kind of remotely up via NFC from this device, gathers my blood sugar data, sends it to the cloud. So yeah, NFC used a lot. If you used it for transit, if you used it for paying, so a lot of sensors and devices in IoT devices. That's actually pretty cool. I will give a shout out to one Azure project. So there's an Azure app called Azure IoT Central, which is a kind of software as a service platform for building IoT applications. You kind of just drag and drop charts and graphs and all that. And we just released a smartphone app for that, where you run it on your phone, actually gathers data from your phone, accelerometer, gyroscope, magnetometer, and sends it to the cloud. So if you just want to kind of see roughly how it works with seeing telemetry data in an IoT Central application, we've got a mobile app that actually captures that. So yeah, you can use your phone as a great example IoT device, which is pretty cool. Pedometer. Yeah, so the pedometer is related to the accelerometer and gyroscope, and usually it's kind of smarts in there that picks up the acceleration and gyroscope data and then actually interprets that into step value. So it's kind of a sensor that combines logic with data from other sensors, kind of bringing it together to give you different values. But yeah, that's a very important one. Yeah, a lot of people use their phone for step counting. Cool, that's good answers there. Yeah, IoT devices, phones are packed full of sensors, IoT devices. Now think about actuators. Let's flip it on its head. What actuators does your phone have? So yeah, sensors convert physical data to electrical signals that are used by IoT device. Actuators, you take electrical signal from your IoT device and converts it to a physical interaction with the real world. So what actuators does your phone have? I mean, I'll start with one, which is the speaker. Opposite of the microphone, converts electrical signal into noise. Any other actuators that your phone has? Yes, it has some kind of vibration unit that vibrates, either direct vibration when it rings, or just haptic feedback, which is kind of more subtle vibration that makes it feel like you're doing things. I can feel like when you're pressing a button down, it feels like the button's going down when it actually isn't, based off vibration. Yeah, LCD. Yeah, the screen. The screen is an actuator. It gives you physical results through your screen. Touch screen, that's a combination of an actuator and a sensor. It senses where you touch, but also then gives you feedback, a visual feedback as well. So it's kind of a combined sensor and actuator. Yeah, that's a really good one. It's one that I don't think we mentioned that in the sensor list. So good catch, Ed. Any other actuators that it has? USB, but yeah, I mean, it sends data over USB, so you can connect other devices to it. There's so many kind of accessories you can kind of add on that do things. USB, I mean, you can add like sensors to the USB port. External microphones, whatever, or output for lights, sound, other things. Yep, that's one. LED as well. A lot of the LED flash that's used on the camera, sometimes that can be used as a torch. Certainly on my iPhone, it's a torch setting. So there's LED. That's one. It's kind of not so many. It's because the phone obviously is more of a visual device. So you kind of get most of the actuator is based off the screen. But yes, it's the screen, the speaker, vibration, and the light, and that's really about it on the phone. But it's still quite a lot. It's still a powerful IoT device that you can use to get data in and get data out. So awesome. Well, we're at time. 10 o'clock here for me in the morning in the West Coast of the US. This is a really great session today. Some great conversation.